What is next? Let's find out. Okay. Two more examples, kind of taking a little bit further. So we're not just doing a derivative for these. In the first example, y equals 5x e to the x. Find the equation of the normal line at 0, 0. Interesting. We're going to find out what the normal line is. And then we're even going to find y double prime. And the second example, determine the x values where the function has a horizontal tangent line. Okay, very cool. Let's switch over here. Example, y equals 5x e to the x. Find the equation of the normal line at 0, 0. So the normal line is the line that is perpendicular to the tangent line. When we're done with this question, this is part A, we'll graph this and we'll be able to see that normal line. It's pretty sweet. How are we going to do this? Well, the equation of the normal line, if it's perpendicular to the tangent line, we first need to know the slope of the tangent line at our point. So let's take a derivative. We need a product rule. As you start using these, really keep your eye out for on your functions, right? Is your function actually the product of two functions? The product rule has a way of kind of slipping past the radar. And if we, get complacent, then we can miss that it's a product rule and we can do something very wrong. So stay diligent, kind of look whenever you see a function, what rules would apply to this if I'm going to take a derivative? So here our product rule would say, okay, derivative of the 5x is 5 times e to the x plus 5x, and derivative of e to the x right there. All right, we got it. 5 e to the x plus 5x e to the x. We need to know the slope of the tangent line at this point. And we're going to use that x value that they tell us. Turns out we don't really care that what they give us the y value, but we don't really need it. We just need that x value. We're going to find y prime at 0. So 5e to the 0 plus 5 times 0 e to the 0. What is the slope of our tangent line at 0? Well, this is all gone. E to the 0 is 1. So that slope of the tangent line is 5. What is the slope of the normal line? So I said the normal line is always perpendicular to the tangent line. Well, perpendicular is the negative reciprocal, -1/5. So there's the slope that we want, and we know it passes through this point. So y minus 0 equals -1/5 x minus 0. And if we clean that up, works out pretty well. Y equals -1/5. Right, I know we have a part B to this question, but let's just take a moment and graph y equals 5x e to the x. See, okay, that's kind of cool. So we're going to be looking for the normal line at the origin. We found it to be y equals -1/5 x right there. Interesting. Okay, so that's coming through and it's actually perpendicular to the function right there. What would the tangent line be doing? Well, since it's at the origin, it'd be just y equals 5x. And if we get rid of the purple, we can see that, yeah, those are perpendicular. And so our red line is tangent. Our normal line is perpendicular. You might think like, okay, so what's kind of the significance of the normal line? The tangent line, moves in the same direction. It's an instantaneous velocity. What's a normal line going to tell us? Well, one application, I bet there's tons more that I'm not aware of, but one application, the normal line would tell you, let's say you were driving in a car, kind of maybe like down this road, like maybe this is a bird's eye view, and you were kind of just driving along, right, on that purple line. The tangent line would be, where the car is pointed at any given moment. So like maybe right at the origin, if you took your hands off the wheel, then the car would move along the tangent line from there, right? If it just kept going straight. The normal line is telling you how much like pull you're getting to the side of the car as you're moving. So there's a little bit of a curve here, right? So you might feel yourself getting pushed, to the outside of that curve. So you're going to feel like it's almost like centripetal force, but like the opposite, because you're getting pushed, well, no, centripetal force, you're getting pushed away. Yes, you're kind of like getting smushed against the side of the car. And here it would be pretty subtle because that's a pretty gentle curve, but, maybe down here, right, you'd really be getting, you'd be feeling some force pressing you out to the edge. Like say if you were to take a slingshot and spin it around, like the rock that's inside the slingshot would be experiencing a pretty significant force along the normal line, like a toy airplane that you might spin around. Okay, enough of that. We don't really do much with the normal line, by the way. It just kind of comes up and we just kind of like, yeah, that's cool. Okay, so part B, we want to find y double prime. Well, we have y prime back here. Let me copy that just for our video purposes. Y double prime, okay. To find y double prime, since we're adding, we can take the derivative of these separately. When we get to the second one though, notice that's another product rule. Same product rules we had before. Well, let's take a look. This derivative, well, it would just be itself. But now we need the product rule again, 5e to the x plus 5x e to the x with that product. And well, that simplifies pretty well. 10e to the x plus 5x e to the x. There's our second derivative. Pretty sweet. Okay, we had another example. It's a cool one. Determine the x values where f of x has a horizontal tangent line. And our function was this 2 minus 1 over x plus 4. Let's pause for a second. A horizontal tangent line. So this came up when we were graphing derivatives. If there's peaks and valleys on the original function, we noted that that's where, like if you have kind of a peak like that, the very top, that tangent line is horizontal. The slope of a horizontal line is 0. So if we want to find the x values where f of x has a horizontal tangent line, we need to find x values where f prime of x is equal to 0. Where would our derivative equal 0? Okay, Well, first thing we're going to need is a derivative. So let's take a look. You know what? Before I go there, I noticed that this has a 1 over x in it. Let me rewrite that. So no derivative yet. I'm going to rewrite 1 over x as x to the negative 1. That's going to make my derivatives go a little bit easier. I guess if you really wanted, you could apply a quotient rule to that, but just think of it this way. Okay. Now, we do need a quotient rule for this. All right, low times d high. Let's see. Well, the 2 would go to 0. The negative x to the negative 1. That negative 1 would multiply by this negative, become positive, and it'd be x to the negative 2. Minus low d high minus high times the derivative of the low. Well, derivative of low here, derivative of the x is 1, the 4 is 0, so that derivative is just 1. And it's all over the low squared. Okay, in this problem, we're obviously doing more than just finding a derivative, so we do need to simplify this. We're going to end up setting it equal to 0 and solving for x. Let's see. I'm going to distribute here and then just kind of see what happens. So x to the negative 2 times x to the negative 1 plus 4x to the negative 2. And then this minus sign distributes. So, yeah, let's keep going. I can combine x to the negative 1s. Looks good. Okay. At this point, we need to recognize it's not simplified, and it's still really not in a good position to set equal to 0 and begin solving. Why is that? Because we have these negative powers of x inside of a larger fraction. Here's what we're going to do. Remember that this is really like 2 over x, and this is 4 over x squared. We can multiply by the higher of those powers. Let's multiply the top and the bottom by x squared, and that will cancel out all of our negative exponents. Let's see how this works. X squared times this, we'd add exponents and get 2x. Here, x squared times x to the negative 2, those would cancel out, and we just have plus 4 and minus 2x squared. Then in the bottom, well, we're just going to think of these multiplying like that. Okay, I think we're ready to set this equal to 0 and solve. 2x plus 4 minus 2x squared over this denominator equals 0. Where does our derivative equal 0? Now this looks like kind of a beast, but it's actually not nearly as bad as it looks at first. This denominator, we can multiply it to both sides, and it's just gone. All right. Cancels out, multiplies by 0. Excellent. For the rest, let's rewrite this with the highest power of x coming first. And we'll think, maybe this thing will factor. We can factor out a negative 2. That would be nice. So minus x minus 2. And I think this even factors further. Let me just keep working right over here. X squared minus x minus 2. Let's see, x. That would be minus 2 plus 1. Get us the minus x in the middle and the minus 2 here. Yeah. So we got x minus 2 equals 0, x plus 1 equals 0. And we got two solutions. That's all we needed. They wanted us to find x values. We got it. I guess if we really wanted to, we could find the y values by plugging back in, but they didn't ask for that here. They just wanted those x values. Let's check out the graph. Y equals 2 minus 1 over x plus 4. Kind of cool. Whoa, okay. Didn't expect that. X equals 2. Okay, so right there, there's a horizontal tangent line. Yep, the tangent line moving across. That looks like that's pretty much, it would have to be the peak of that bump. Makes sense. And x equals -1. Yeah, that's at the very bottom of that curve. See that? There's a horizontal tangent line there. There's this other branch, but it didn't produce an x value. Makes sense. You know, it's kind of like asymptotic. So it's like coming up to the x-axis. So it's always increasing. It never actually comes to a peak, and then it drops off. So yeah, there's nothing here, but we got a bottom there and a top here. Pretty cool. Okay. I was wondering, is there anything else left to our section? I forgot. Yes, stick around. Next video is the proof of the product rule.